Welcome back. Since we are talking about imatinib, let's talk about the synthesis of imatinib and analogs. And as we mentioned earlier, this is the chemistry part of the pharmaceutical chemistry. The starting material is this pyridine analog or pyridine compound number 1. The first step, or actually, sorry, the first and the second steps, those two steps is just to introduce the first anilino group, okay, or the central anilino group, this one, okay. Then it's just reduction of the aromatic nitro group to aromatic amine. As you can see here, this is NO2 will be reduced using palladium over carbon to NH2. Then the just acylation of this amine to form the amide analog. The AR group here, that's called aryl AR. This represents the phenyl ring and the piperazine ring of imatinib. You can go and check that in the imatinib structure. All right. We talked about imatinib, so how about the second generation BCR-ABL inhibitors? All right. Like the nilotinib, the dasatinib, and the bosutinib. Okay. These, the nilotinib and the dasatinib, both of them have better or more affinity toward the enzyme if you compare them to imatinib. Dasatinib and bosutinib inhibit two protein kinase targets, the ABL and SRC, which is a way to overcome resistance, okay? Because as you can see from these figures, all of those, nilotinib, dasatinib, and bosutinib, all of them have that important interaction with threonine 315. This one, and even this one, okay? So you need that interaction, which means if this threonine mutated to isoleucine, as we saw earlier, you will lose this interaction. So one way to overcome the resistance is to make inhibitors that inhibit two protein kinase targets, ABL and SRC, just like in dasatinib and bosutinib. Okay, nilotinib, dasatinib, and bosutinib are inactive against the T315I mutant, as I just mentioned, because they need this interaction to be active. So if you lose the threonine, you lose the hydrogen bond and you lose the activity. Isoleucine is unable to form the hydrogen bond formed by threonine. The isoleucine is larger than threonine and has steric clashes with inhibitors. So that's the two reasons behind the loss of activity. Okay. Another second generation is the ponatinib. You see the structure of ponatinib here with the binding interactions. It's a type 2 kinase inhibitor, just like the imatinib. It's effective against native AVL protein and various mutants, including the T315I mutant. Okay, why? Because you don't have a group here that can form hydrogen bond with threonine. So even if you change the threonine to isoleucine or phenylalanine, you're still able to form this hydrophobic interaction with the phenylalanine or the isoleucine. The alkyne group, the one that we just mentioned, avoid steric clashes with isoleucine and the T315 mutant and allows access to the hydrophobic selectivity pocket guarded by the gatekeeper residue, okay, because there will be no steric clashes. It's alkyne. The alkyne is just linear, okay, it's planar. Alkyne also forms van der Waals interactions with the isoleucine and phenylalanine. The isoleucine 315 and phenylalanine 382. The piperazine ring, the one at the top here, this one, is protonated and aids water solubility, just like the piperazine ring in imatinib. And it also interacts with aspartate 400 by an ionic bond. You see the bond here, and also forms van der Waals interactions with various residues like aspartate 381, valine 289, isoleucine 360, and phenylalanine 359. The bicyclic ring forms a hydrogen bond to the hinge region. And we mentioned the moment we start talking about these inhibitors, the kinase inhibitors, especially the tyrosine kinase inhibitors, that you need a bond, a hydrogen bond at the hinge region. All right. Other inhibitors like the GNF2 and the ON012380. These doesn't interact with the with the enzyme at the ATP binding site. These interact with the enzyme at other sites. It's an allosteric inhibitors. You remember when we mentioned the types, we said that there are some inhibitors, we call them the allosteric inhibitors because they don't interact at the ATP binding site. It interacts somewhere else. Like the GNF2, it's an allosteric inhibitor of BCR, doesn't bind to ATP binding site. It stabilizes the inactive form of the enzyme. Okay, so it prevents activation. It binds to an autoregulatory cleft in the enzyme, hence the name allosteric inhibitors, and it's a potential agent for treating leukemia. Or actually, this might be the first agent that targets leukemia specifically. Okay, and this agent is still in clinical trials. While ON012380 binds to the protein substrate site, if you remember earlier, we said that the clinically active agents, which means the agents that are in the market nowadays, they interact at the ATP binding site. But that doesn't mean scientists cannot do studies on agents that binds to the protein substrate site, like this one. It binds to the protein substrate site, this, and currently it's under study. It's under clinical trials. All right. We talked about the tyrosine kinases. We talked about the imatinib, gefitinib, their analogs, the first, second generations of them. Now let's move on. Let's talk about the cyclin-dependent kinases, the inhibitors of cyclin-dependent kinases. So what are the cyclin-dependent kinases? or what they like to call them, CDKs. These are involved in control of cell cycle and are overexpressed in many cancer cells. And if you remember in the introduction, when I told you that you need to read the cancer introduction in the reference book, okay, you will find some information about the CDKs. The CDK is a serine threonine kinase. Okay, it's not tyrosine kinase, it's a serine threonine kinase. It's activated by cyclin. That's why it is called cyclin dependent kinases. It's inhibited by cyclin dependent kinase inhibitors. Well, that's obvious, right? Synthetic inhibitors bind to the ATP binding site of CDKs, just like the inhibitors of the tyrosine kinases that binds to the ATP binding site of the CDKs. Okay, the first example on those inhibitors is the flavoperidol. You see the structure here of the flavoperidol, and the roscovitin, or what's called the silicyclib. You want to call it roscovitin, silicyclib, it's up to you. Okay. The flavoperidol contain a piazopyran ring, a piperidine ring, and a chlorophenyl group. The piazopyran group, this one has a hydrogen bond donor and hydrogen bond acceptor, and I think now you know where these are going to interact with the enzyme at the hinge region. Okay. The flavoperidol is also known as the alvocidib. As I said, call it flavoperidol, alvocidib, it's up to you. The benzopyran ring system bind to the adenine binding region. What's the other name of the adenine binding region? The hinge region. Okay. The piperidine, this group, bind to the region occupied by the first phosphate of ATP, okay, which means it's a polar group. It's a hydrophilic group. Okay, the chlorophenyl group, on the other hand, lies over the ribose binding pocket. So this one is going to go deep in the enzyme. This one is going to go on near the cleft, and the chlorophenyl at the ribose binding pocket. Roscovitin, on the other hand, shows selectivity for CDK2, which is good. Both agents are undergoing clinical trials now. It is also important to mention that flavoperidol is a semi-synthetic compound, which means it's a derivative of a natural product or a naturally occurring compound. All right. Other inhibitors like the palbociclib, the ribociclib, and the abemaciclib. Okay. All of these are new agents, as you can see from the approval date. The first one was approved in 2016, and the other two were approved in 2017, which is new if it's compared to other drugs or other medications. These are selective for CDK4 and CDK6 and approved for the treatment of certain types of breast cancer. So if you see the trend here that we are going toward agents that are selective toward certain types of enzymes, which makes them selective toward certain types of cancers, right? And that is good because that decreases activity. All right. Now let's talk about the kinase inhibitors of VEGFR, the vascular endothelial growth factor receptor. Okay, so what is the VEGFR? As I said, it's short for vascular endothelial growth factor receptor. It's associated with angiogenesis. And if you want to know what angiogenesis mean, you should go back and read the introduction. Inhibitors of angiogenesis would starve cancer cells of nutrients and inhibit the growth of the cancer. And that is obvious, I think, right? VEGFR is structurally similar to several other tyrosine kinases. So again, it's a tyrosine kinase. Current inhibitors are multi-kinase inhibitors. So there is no selective inhibitor for the VEGFR, but there are some inhibitors that inhibit different kinases. Among them is the VEGFR. Okay. Examples on clinically improved agents that include VEGFR as a target: sorafenib, sunitinib, pazopanib, vanditanib, axitinib, cabozantinib, lenvatinib, vatalinib, and regorafenib. I know, weird names, but that's how they call them. These are examples on some clinically approved agents that include VEGFR as a target. And as you can see, includes, which means there is no specific one just for the VEGFR. Okay. And this is the end of this part. We will continue with this next part later.